brief introduction, D.1. All right. So we applied brute force method in our polynomial evaluation problem. Yeah. Here, so let me just describe this method. Yeah. So there are several properties for this method. Yeah. First, it's a straightforward approach. Yeah. You just work on the problem directly without doing any special technique. Yeah. Without using any special technique. Yeah. Yeah. You can always apply it to a problem. Yeah. Usually it may not be good, yeah, but you can always apply this method to any problem. Why? Yeah. So you can think in this way, the brute force. We work on the problem directly. So you think about, given a problem, given a computing problem, when we need to solve that problem, we need to consider all the possible cases, right? All the possible cases. The number of cases we will have for a typical computing problem, usually the finite number, right? Think about typical computing problem. Only finitely many different cases you need to consider. For example, sort an array with n elements. How many cases do you have? How many number of different cases for an array with n elements? N factorial. N factorial. We know it's a big number, right? N factorial. It's very big. N factorial. But it's finite, right? It's finite. Brute force method, the worst you can do, you exhaust all the cases, right? Yeah, it's really bad. It's really bad, but at least you can work on it, the brute force method. Okay, yep. Yeah. All right. In general, it is not the best algorithm, we know. Yeah. So because you do not apply any technique. Okay. Yeah. In general, it's not the best algorithm. The reason is if you go through all the possible cases, that's not efficient. That's not efficient. Yeah. Better way, we can eliminate large number of cases. Now, we want to eliminate as many cases as possible. Okay? If you can apply some special technique, method, you can eliminate large number of cases from all the cases. Then you improve a lot. Then you improve a lot. Yeah. Yeah. All right. It is usually used as the starting point for more advanced algorithm. As a starting point. Yeah. Because at the beginning, we do not have any idea how to solve the current computing problem at the beginning. Because we do not understand the problem well. Only when you understand the problem very well, then you need to have some creativity to find a smart solution that can eliminate a large number of cases. So you only need to work on relatively small number of cases. Then it's more efficient. Yeah. So that's the general discussion. Okay. Yeah. All right. Yeah. So as a starting point, because we need, so when we work on it, do experiments. At the beginning, we do some experiments. When we do experiments, we get experience from it. When we get more and more experience, we understand the problem better and better. When you understand the problem better, you can discover some critical properties. Critical properties. Remember, that's important. After you can discover some critical properties, then you can, take advantage of those properties to help you reduce large number of cases. Yeah. All right. The efficiency difference. Yeah. So the brute force one, and later you get a much better algorithm. Then you compare efficiencies of these two methods. As our project one, we compare two methods. The first one, brute force. No, because we do not apply any techniques, right? We just apply addition, multiplications directly. That's the brute force method. Right. Yeah. But, all right, 3 students came in. Yeah, I need to add Maimoon, Sullivan, and Amanda, 3. Yeah. Oh, last time you also came in? Okay. Oh, all right. Oh, okay. Yeah, all right, yeah. So the difference of the efficiency, very big. So the first project, I let you feel about it. Yeah. Okay. Huge difference. All right. Yeah. So that's our example. Yeah. So you can see the time you spend. Yeah, you need to spend a lot of time. The time you spend to develop much better algorithm, it will save you a lot of time in future when you apply it many, many times. Yeah. Because after you develop it, you implement it, your program could be used thousands of times, right? Yeah. So the improvement is big. Yeah. All right. So let's revisit our sorting problem another time. Remember at the beginning, I said we may need to solve the sorting problem 6 or 7 times. Yeah, here, the second time. Yeah. We try to use a different way to solve it. Our second method to solve it. Yeah. All right. Yeah. The same problem. Yeah. But there is the first question I like to explain a little bit before I start solving it. Why we need to solve it another time? We already have a solution, right? Why we need to solve another time? Yeah. One of the answers could be because we want to improve it. One of the answers, we want to improve it. One of possible answers. But sometimes we have some other considerations. Yeah. Even if the efficiency is good enough, sometimes we like to consider a different solution. One possibility, because for the different solution, our emphasis could be different. Yeah. Because for one problem, there are several different aspects we can put our focus on. All right? Yeah. For example, let me give you the simplest case. For example, For one solution, we want to focus on the worst case. We want to make the worst case as good as possible. You know, the efficiency for the worst case as good as possible. That's one of the considerations, right? Yeah. Our focus, we put on the worst case. Another consideration, we put our focus on average case efficiency. The worst case could be bad. Yeah, we take it. The worst case could be bad, but we want to get the best average case efficiency, right? So you can see for different considerations, our solutions will be different. Yeah, so that's the reason. So we need to consider different solutions. All right. But there is another important reason. Well, we work on multiple solutions for the same problem. Another. Yeah. That's from the problem-solving point of view. Problem-solving. Yeah. We know the problem-solving skills, very important, right? Yeah. Here we talk about computing problems, not the general problem solving, computing problems. You need to apply many methods, right? Problem solving, many different methods. Yeah. But the question is, the problem-solving methods, how do you carry the problem-solving methods? Suppose there are many problem-solving methods. We know the problem-solving methods, they are not objects, right? They are not concrete objects you can carry in your bag somewhere, right? They are thinking in your mind. But your memory, we know our memory usually not very good, right? So we may forget a lot of things. Yeah. So how do you carry the problem-solving methods? Yeah. Here, another point of view, our view, another view. We use specific computing problems to carry problem-solving methods. For example, sorting problem is a computing problem, right? Sorting, sort and array. So this sorting problem can carry 6 or 7 different problem-solving methods. How about that? 6 or 7 different problem-solving methods, because we have that many solutions. So this one, okay? So after we study all those solutions, yeah. No. So you can understand in this way, this problem-solving method, we can treat it as some container, abstract container. It holds 6 or 7 different solutions. And those solutions we can use to solve other related problems. So that's another useful way for us to, to help us get better in problem solving. Yeah. All right. Yeah. So that's another view. Yeah. All right. So here, now let's try to solve this problem differently, in a different way. Different way, we should not use the same thinking of our first method, selection sort. Remember our first sorting algorithm, selection sort. So this time, we should not use the selection way. So every time we find the minimum, that's the key step of the selection sort. So this time, we try to find a different property for the solution. All right. What's that property? Special property. So first, you need to do some observation. You need to, look at your data carefully and try to explore some important, useful property. All right. Here, let me use a diagram. So let me draw this diagram. So we try to find some useful property. So this time, remember, our goal, we want to make our data in ascending order. In ascending order. That's our goal. Okay? Yeah. If the given elements are arranged in ascending order, then we complete the solution. Yeah. So at this time, let us pay attention to the order information. Pay attention to that order information. Okay? Yeah. If some of the elements are not in ascending order, think about that. Some of the elements not in ascending order. Let's study this typical case. Yeah. Let's consider here two elements. Here I draw two adjacent elements. Yeah. Later, not necessary two adjacent. Okay. Yeah. Two of the elements. Let's examine the order between these two elements. Order between these two elements. Yeah. We can assume distinct. Yeah. Let us simplify our data slightly. Distinct elements. Okay. Yeah. So only two possibilities, right? AI less than AI plus 1 or AI greater than AI plus 1. Only these two cases we need to consider. Yeah. The first case, AI less than AI plus 1, that's in ascending order, right? In ascending order. Yeah. So that means we do not need to do anything, right? Yeah. Already in ascending order, so we're happy. Okay. The second case, not in ascending order. AI greater than AI plus 1. We need to do something, right? Yeah. If we do not do anything, then we cannot change the order. Okay? Yeah. So for the second case, that state, that state causes some problem. So we need to fix that problem. Then we can get closer to the final destination. Ascending order, that's our final destination, right? So we like to do some work to change the order to make our data closer to the final destination. How about that? That understanding. That's our understanding. Okay? Yeah. All right. So here we want to really work on the case that a pair of elements are out of order. Any pair. Okay? Yeah. Because if we can find any two elements, yeah, we treat it as a pair. If these two elements are out of order, swap operation, right? Swap operation, we can fix that particular pair out of order problem. How about that? Yeah, swap operation. Fix just one out of order pair problem. Only, yeah, just that one. Okay, yeah. So you can see with this understanding, yeah. So you can see we spend so much time to understand the problem. When we do analysis, we do understanding like this. All right. Observation for critical property. So we summarize the critical property we discovered here. Okay. If the array is not sorted, yeah. If it's sorted, yeah, we just move on, right? If it's not sorted, there must be two adjacent elements that are out of order. Is it correct? Two adjacent, yeah. Here, I put two adjacent elements. All right. So first, let me circle this out. All right. First, let us skip this adjacent word. Okay. Skip this adjacent word. Then it's better to understand. All right. If the array is not sorted, there must be two elements that are out of order. That's correct, right? Yeah. Otherwise, if any two elements are in order, then already sorted. Okay? Yeah. So our first round understanding, yeah, there must be two elements in the array must be out of order. Then we can say the whole array is not sorted. Yeah. All right. Second time, after we understand, we get this step, we'll move one step forward. Let me put this adjacent into it. Make this statement stronger. Okay? If an array is not sorted, there must be two adjacent elements that are out of order. This time, two adjacent. Okay? Yeah. It is a little harder to understand than the first one, but we can understand. So you can think it this way. Think about if any two adjacent elements are in order, any two adjacent elements are in order, by transitivity, the whole array must be in order, right? Think about it. If any two adjacent elements are in order, in ascending order, okay? Yeah. Then by transitivity, what's transitivity? Yeah, let me recall. I remember I wrote once before. All right. A less than or equal to B, B less than or equal to C, then it implies A less than or equal to C. Okay, this is transitivity property of inequality. So now if you cannot find any two adjacent elements are out of order, that means any two adjacent elements are in order. Then by transitivity, the whole array is in order. It's sorted. Okay, yeah. Because our assumption, the array is not sorted. So based on our assumption, you have to have at least one pair of adjacent elements that are out of order. Yeah. So that's the critical property we discovered after our analysis. Then our solution will be based on this observation. Yeah, because you can find an adjacent two elements out of order. Now you just fix that pair by a swap operation. Yeah. Yeah. All right. Yeah.
If you swap it though, couldn't it still the odd order something else.
Yes. Yeah. Yeah. So it only solves the problem locally, that position. But for other places, you need to check, detect, solve all the out of order places. Apply swap operations everywhere else to fix the out of order problem. Okay? Yeah. That's the solution, basic idea of the solution. Yeah. All right. Here, let me give you the reference in the textbook. Yeah. But for our discussion, I here to this, because here, this out of order, this property is important. So we use a concept. The concept here we call inversion concept. Here, let me define this inversion concept to describe that out of order property. All right? Yeah. A pair of elements A, I, A, J, this pair, here you can not necessarily adjacent. Yeah. When we define this inversion, we do not require these two elements are adjacent. Yeah. So it's a general concept. Yeah. It's called an inversion if A less than, if I less than J and AI greater than AJ. Yeah. So you can see I and J, the subscripts. The subscripts are in ascending order, but the values of these two elements are out of order, yeah, in different order, yeah, in descending order. Yeah. So we call this pair of elements an inversion concept. Yeah. So then in our critical probability, the statement, we can use the inversion concept. If the array is not ordered, the first version, if I remove that adjacent word, yeah, then I can say there must be an inversion. Okay? If an array is not sorted, then there must be at least one inversion. Right? Yeah. Here, the inversion, we mean the global inversion. Global inversion. Okay? All right. The second version, that is the first version. Second version, if the array is not sorted, there must be an adjacent inversion. That's the second version of our critical property. There must be an adjacent inversion. Stronger statement, yeah, but this time not global, it's an adjacent inversion. It's also correct. Yeah. 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 All right. So now with this understanding, we're halfway in our solution. Yeah. Halfway. So you can see our goal, we want to reduce the number of inversions, right? Yeah. Sorting, our understanding of the sorting, we just want to reduce the number of inversions. So every time we reduce inversion by one, eventually we reduce the number of inversions to 0, then the whole array is sorted. How about that? When the inversion number becomes 0, it is sorted. All right. So we just scan this our array again and again. Every time, whenever we see an inversion, we swap. two elements. We swap two elements, then we fix that inversion, right? So that inversion is gone. After one swap operation, that particular inversion is gone. Then we try to find another inversion and the swap gone. Okay, so we keep reducing inversion pairs. All right, yeah. At the end, we remove all the inversions by swap operation. Then we're done. How about this idea? Okay, yeah. So let's implement. Yeah. All right. If the array is not sorted, there must be an inversion. Yeah. If the array is not sorted, there must be an adjacent inversion. Yeah. Our algorithm, we want to build using the stronger statement, stronger property. Yeah. We do not use that weaker property. The first one is the weaker property. The weaker one, because you need to detect global inversions, right? That's not efficient. Global inversions. For the stronger version, we only need to detect adjacent inversions. Much easier than the global inversions. So we use the second version property. All right. Yeah. So we change our view from global view to local view. Global view, that means you need to do more work, right? Yeah. Because you need to put your resource globally, right? Too much resource. If we only apply our resource locally, yeah, we can save a lot of resource. Think about that. Yeah. So global view to local view. Okay. Yeah. So that's another commonly used problem-solving method. Yeah. All right. Now, implementation details. So we have the, high-level understanding, but now we want to organize our data well to fix the implementation details. Yeah. All right. Swap operation. How do we apply swap operation in an organized way? Yeah. Not a messy way, here, there, very messy. You cannot keep track of them, right? So we want to keep track of, our data already in order, right? Yeah. If the data already in order, then we do not want to do redundant checking, right? If data already in order, why you need to do the, inversion checking? We do not need to do inversion checking on ordered data, right? Yeah. So we need to keep track of our ordered data. Okay. Yeah. All right. Implementation idea. Remove all the local inversions by local swaps. Yeah. Or here the local, we can use a better word adjacent. Yeah. Because adjacent even better than general local. Okay. Yeah. Adjacent. So remove all the adjacent inversions by adjacent swaps. Yeah. So we can improve this sentence. All right. The procedure. Step 1, start from first element for each scan. Yeah. So we scan this array from the first element to the last element for one scan. When we scan, we consider an adjacent pair of elements. If we find inversion, we swap them. If no inversion, we move to the next adjacent pair, and so on. Okay? Yeah. All right. But after one scan, what's the improvement after one scan? Yeah. we do swaps one by one from left to right. Now we want to consider the result after one scan. After we finish one scan, where is the maximum element after one scan? We scan from left to right. Now you put your focus on the maximum element. Where is it? Maximum element. Right. So after one scan, the maximum element must be at the end of the array. Must be. Then, remember we have a special word for that term, in place. Okay? So after one scan, the maximum element must be in place. Maximum already in place. So our second scan, do we need to look at maximum again? No, already in place. Why you touch it? Okay. Eliminate it. All right. So the second time when we do the scan, we ignore the maximum element. Yeah. So we cut off that maximum element. We treat the remaining part, the current array. The current array. So the second time we scan the current array from left to right. So we put the maximum of the current array at the end, right? Yeah. So we put a second element in place, and so on. The third time, third element in place, and so on. Okay? Yeah. At the end, we put all elements in place, right? Then we sort it. Yeah. That's the idea. Okay? All right. Yeah. So, yeah. Here, yeah. All right. Stop at the first. Yeah. So here, the step 3, because after we remove those in-place elements, we avoid redundant inversion checking, right? Yeah. You do not need to check inversion on those elements that are already in place, because we know there is no inversion. Do not do anything on in-place elements. So stop at the first in-place element. Yeah. The first one, because we know starting from the first in-place element, the remaining all in place. All in place. So you stop right before that first in-place element. Yeah. We can use a counter to tell us. Yeah. So that's easy. Yeah. All right. Yeah. So then our solution. So we have the solution. Yeah. 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 So you can see there is one element in place for every scan. That is the end. So the in-place element of each scan appears at the end of the current array. Yeah. So the current array is a subarray that excludes all the in-place elements. Yeah. So that's the some basic facts in our algorithm, in this algorithm. Yeah. All right. So now, visual imagination. Yeah. So we complete. So this solution, yeah. So this one, the swab looks like a bubble moving to the right. Yeah. So this people call the bubble sort. Yeah. You heard of that? Right. Yeah. This is the algorithm you learned in CS3250. Data structure, that one, you learned the bubble sort. Yeah. I taught that class once before. Yeah. So, yeah. I remember that. But at that time, if you can recall, at that time, basically, you just write a code to do the sorting in this way, right? You didn't do analysis like, what are we doing here, right? Yeah. So you can think about what we went through, we did a lot of problem solving thinking. At that time, You didn't do it. Problem solving, thinking, right? Yeah. Yeah. So here, we want to learn the problem solving thinking, because in the future, you need to use all these thinking you learn from this class to solve your real world computing problems. Okay, yeah. All right. So that's the bubble sort, our second sorting algorithm, bubble sort. Yeah. Efficiency analysis is similar to that of the selection sort. Yeah, similar to selection sort. But selection sort, that the difference, the key difference. Yeah, here you can already see the key difference. For the selection sort, every time we put the minimum of the current array in place. The bubble sort, every time we put the maximum of the current array in place. Yeah. Other than that part, yeah. The scan way, yeah. Quite the same. And when you count the number of comparisons, also the same. Yeah. The first round, the first scan, you need n-1 comparisons. The second scan, n-2 comparisons, and so on. Yeah. So, yeah. So what is the basic operation? If we go back to check the concept, basic operation, because here you have comparison operation, you also have a swap operation. Yeah. So now, can you see which one is the basic operation? Comparison or swap is the basic operation. Do you do comparison more or you do swap more? Which one you need to do more? Swap? Yeah. Think about this. When you detect if two adjacent elements are in order, are an inversion or not, you do one comparison, right? But if they are in order, do you do swap? Yeah. So that means sometimes you do swap, sometimes you do not do swap, but you always need to do comparison. So you use comparison more, okay? Yeah, because you use comparison more, so we treat comparison as the basic operation, not swap. Not swap. Yeah. Because if the array is already in order, there is no swap. Right? There is no swap, but you need to do comparisons. Okay? If an array only has one adjacent inversion at the end, you need to do a lot of comparisons, but you only do one swap operation at the end. Yeah. Think about that. Yeah. So that's the reason comparison is the basic operation. All right. Yeah. D.2, string matching problem. All right, string matching. Yeah. From this name, I think you can guess what we are doing, what we are going to do. Yeah, let me give you the problem. Problem number 5, string matching problem. Given a string of n characters, so we call it text, a block of text, okay, string, yeah, or document. Yeah, you can treat it as a document, okay, yeah. And the string of n characters, we call it pattern, all right, with m less than equal to n. Yeah, all right. I will go find a substring of the text that matches the pattern. Substring. Yeah. M character substring. Somewhere in the text, in that body, in that block of text. Yeah. Exactly the same as the pattern substring, content. Yeah. Yeah. So you can see it's a very simple computing problem, but very useful, right? Keywords-based search. You can see this one is the keywords-based search. You use a lot. People use a lot. Keywords-based search a lot every day. Yeah. Yeah. Here, it's a basic computing problem. Okay. Yeah. All right. So let's first time to solve a brute force. Brute force. Okay. Yeah. Yeah. All right. Find its location. What do you mean its location? Yeah. A substring. Yeah. Yeah. So there is a width of that substring. What's the location? Location of its first element, first character. Not the last, not the one somewhere in the middle. Yeah. Location of its first element, character. Yeah. The index or the subscript index of its first character. Find that location. All right. Index I of the leftmost character. Yeah. That's our definition of the location of a substring. Okay. Yeah. All right. First solution. Yeah. First, we need to use mathematical representation to describe, If we do not use mathematical representation, then we can only do talking, right? Yeah. Using words, do talking. It's hard to do accurate logical reasoning. Yeah. So we need mathematical representations. Yeah. All right. Yeah, here we just use straightforward thinking. Yeah. For them. Yeah. All right. Yeah. Yeah, because after we have some good mathematical representation, then we can apply certain mathematical tools. Yeah. So some of the tools could be very powerful tools we can apply. Yeah. Otherwise, if we do not have the mathematical representation, then we cannot apply any tool. Yeah. All right. Text. Yeah. We use this representation. A sequence of character variables. Yeah. Here, each one, T0, T1, T2, each one is a variable. Yeah. Yeah. A sequence of characters. Yeah. With subscripts from 0 through n-1. Yeah. Pattern P0, P1 through Pm-1. Yeah. Then we need to represent the matching state. Yeah. When you get a match, how do you describe a match state? Yeah. Right. Here, we represent in this way. Suppose at location I, we have a match. We find a match at location I. Yeah. That means Ti equals P0. Yeah. The first location, it matches the first character in the pattern. T sub I plus J equals P sub J. Okay? Yeah. If you move one position to the right in the text, Then you also need to move one position to the right in the pattern, and so on. Now, okay, moving character by character. All characters in corresponding positions are matched. Yeah. Like this. So then you get a match. Okay. Now, so with this description, if you do checking in this way, that's the brute force method. If you do checking in this way, that's the brute force method. Yeah. If not brute force method, you do not check all the possibilities. Here, basically, you check all the possibilities. If it's not brute force, you find some smart way you can skip. Some of the cases, you do not need to do checking. You know, it's impossible to get a match. So you can skip. That's the advanced algorithm. That advanced one is described in our textbook. Very hard, very, very hard to understand. Yeah. But here, I just give you an idea. Brute force, you check all the possibilities. Advanced algorithm, you can do smart way. You can do fast jumping. Okay? Jump faster. Okay? Yeah. So then your algorithm will be faster. Because when you see something special, you know you can jump. When you detect some special property, then you can jump. Okay? So you keep doing things like this, but understanding part is hard. Why you can jump? Yeah, it's hard to understand. How long you can jump? It's hard to understand. Okay? Yeah. All right. So strategy. Yeah. So here, let us just do this brute force way. Yeah. Guess and verify. Yeah. Here, I like to do some simple operation. Yeah. But although those operations are simple, but I want to show you this guess and verify strategy. Yeah. We already used before, right? Remember at the beginning of the class, we do this, guess, verify a few times. Yeah. We guess something, yeah, but it may not be accurate. So then we verify it to fix it. Remember when we count the number of additions, right? Yeah. So we guess and verify. Yeah. Here. Yeah. Also remember when we find the minimum of the array, we guess and verify, right? Yeah. Here we do the same thing here. Yeah. Thinking. Yeah. Can we exhaust all such M substrings? No, brute force. No, we exhaust all the possibilities. The answer is yes, because finite many M substrings, right? There are finite many M substrings in the given text. So we can exhaust. Yeah. Yeah. But here we need to count how many M substrings. Total. You need to know that number. Total number of M substrings. So then we do checking one by one. The first one, second one, third one, and so on. Yeah. Every time extract an M substring from the text with consecutive characters, then we do comparisons. Then we do comparisons described here. If there is one with no matching, we can move to the next substring, M substring. Yeah, because if one of the equality is not true, you don't need to check the remaining pairs. Yeah. You can move to the next M substring. Yeah. Compare it with the pattern for a possible match. So now, how many such M substrings? Can you do some estimate? how many such M substring. Yeah. Use these numbers. Our text has N characters, and our pattern has M characters. Can you use N and M to give N by multiplication, division? It only count the number of M substring. Division, it may not be integer, right? Think about it. Yeah. Division, it may not be integer. Yeah. The number of M substrings must be an integer, right? Yeah. All right. So here, let me draw a diagram. Yeah. This whole line, N characters, that's the text. All right. Then M substring, this small line segment, M substring. Now, so this is the first one. We want to move the second one, third one, and so on. The last M substring is this. Can you estimate how many M substrings you can get in this way from beginning to end? Definitely less than M, right? Less than M. Yeah. Because you can think about the last one, all these places, because you cannot have more M substrates after this part, right? Yeah. Think about what's the number? All right, guess and verify. Yeah, you give me the first guess. That's important. Guess one as closer as possible. Your first guess, always try to make it as closer as possible. So you give me the guess number N minus. Our second step, verify it. Because it may not be correct, right? Yeah. Yeah. Nobody can guarantee your guess is always correct. So to get, all right, verify step. Remember, we use simplest cases to do verification. Simplest case. Here, can you imagine what's the simplest case for this problem? Simplest case.
That is only one character.
Yeah. 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 All right. Yeah. 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 So the simple here, how about N equals N? The text and the pattern, same length. Same length. In this case, how many M substrings? One, right? But from your guess formula, 0. Different, right? So fix that difference. Difference is only 1. So fix that difference plus 1. Plus 1. No, because the answer should be 1, not 0. You just plus 1. So guess and verify. This strategy. Okay? Simple, effective. Yeah. All right. Yeah. Okay, so we complete this step. All right. Yeah. Okay. Yeah. All right. Answer. Yeah. Next. Yeah. We have 10 something minutes. So next. 10 minutes. Implementation details. Just a little more work. Yeah. I try to complete this topic. A little more work. Okay. All right. Yeah. So now we need to do implementation. Yeah. So we know the total number of M substring, M minus M plus 1. Yeah. And here, another question I want to ask you here. Yeah. Look at these locations for our text characters. The first M substring. So we know all those character locations for the first M substrings. All right, yeah. And index of the substring, the location of the substring I equals 0. Okay, yeah, all right. And in our implementation, we want to do a for loop. For loop. So the starting point of your for loop, I from 0, but what is the last I value? The last M substring location. T question mark. Last. So you say something, right? N minus 2 minus M. N minus 2 minus M. All right, let's see. Yeah, let's see. Yeah. Let's do some simple calculation and see if it's correct. Yeah. All right. How to figure out the subscript? Let us use an X variable to represent the X variable. X. We need to find this X value. Then we can write our for loop. Yeah. All right. Here we use this invariant idea again. Remember, I talked about this invariant idea before, right? In that chessboard. Remember the chessboard? We use this invariant idea, you know, the size, K by K size. Then the number of squares, such squares, 9 minus K squares. Yeah. These two numbers added together is 9. K plus 9 minus K equals 9 for all K. This 9 number is invariant because it never changes. Number than 9 never changes. Here, we will use the same idea here to help us find this X value. But how to find that invariant? Yeah, that's the hardest. How to find that invariant? This idea, very important. All right, so here, let me give you the property to figure out this X value. All right. Here, what do we have? What do we have? Yeah. We move M substring along the line, right? Every time we move our M substring one position to the right, okay? But the number of characters of our M substring always fixed, right? We never change. That length always fixed. When you move, that's invariant, right? It never changes. Something when you move, but that quantity never changes. That's the invariant. Here, look at this invariant. This difference of two end subscripts of each substring. It never changes, right? Yeah. The last subscript minus the first subscript for each M substring. It never changes, right? Yeah. When you move, never changes. So we use that one, that number as the invariant to help us set up equation to find that X. Yeah. So that's invariant, find X. All right. Yeah. Because for the first M substring, that difference is M minus 1. That's easy for the first M substring, M minus 1. Okay. Then for the last M substring, the difference should be the same. right? The difference also, the difference we represent. M minus 1 minus X should be the same. Yeah. So we set up this equation. How about that? The difference for the first substring equals the difference of the last substring. Yeah. Because the length is fixed. The length is fixed. Okay. Based on that. Yeah. The difference plus 1 is the length, right? Yeah. The difference plus 1 is the length. Yeah. But it's fixed. Yeah. All right. Solving for X after some simplification, X equals N minus M. Look at this. N minus M. It's not a guess, right? Yeah. Here we know it's correct. It's not a guess. Okay, by rigorous logic reasoning. Yeah. So it's simple. Yeah. In this question, it is simple. Yeah. But this idea is important. Invariant idea. It is important. Yeah. Later, I will, because I would like to let you practice a little bit, this invariant idea. Invariant idea. Yeah, let me see how many minutes. Yeah, I have 4 minutes. Yeah. For this question, we're done, right? Yeah, because implementation, after we get this first value I equals 0, last value I equals M minus M, we just write a for loop. In each iteration, we do character by character comparisons. Yeah, that's the implementation. So we are done. Okay, all right. But, all right. Here, I'd like to give you one puzzle question. So practice this invariant idea, this interesting invariant idea. So I hope I have enough time to, give it. Here we consider chessboard, a chessboard. You know chessboard, right? Yeah. 8 by 8 squares, 8 by 8. Yeah. So here I cannot draw 8 by 8. I just draw this many. Okay. Chessboard. And the squares in white color and the black color, right? Remember the pattern of the colors, white, black, in this pattern. Sorry, yeah. Last one. Yeah. All right. Now, the question. This board, I cut off 2 corner squares. Yeah. I cut off. These 2 squares are gone. Okay. So I throw away. I cut off these 2 squares. So the remaining chessboard, and I want to use domino cards. You know domino cards, right? Domino, something like that. Yeah. So each domino cards to a rectangle containing 2 adjacent squares, right? 2 squares back to back. So let's assume one domino card can cover 2 adjacent squares here. Okay, domino cards. All right. Now the question, can you use 31? Yeah, because after we cut off, we throw away 2 squares. There are only 62 squares, right? 62 squares. The question is, can you use 31 domino cards to cover the remaining of the chessboard? Think about it. If not, Why? Explain to me. Why you cannot? If yes, yeah, show me how to cover it. If not, you need to explain why you cannot. Okay? This puzzle question. This puzzle question, I can tell you the goal to give you this puzzle question. Practice this invariant idea. There is some invariant idea. If you discover, you can find a solution. All right, that's it. Yeah.